Sentite? 1, 2, 3.
Scrivetecelo in chat, se sì.
Buongiorno, ci sono problemi tecnici. Can you hear us? Okay, I can go. Okay, thank you very much. Thank you for the introduction. Thank you for coming. It's a great pleasure to be here, of course. And this is the right display. Is the full screen or? Okay, great. Thank you very much. So let's start. I will today I'll tell you a few things about what we started to do in the last 4 or 5 years, probably, maybe a little bit more. But I mean, the particular application that I'm going to speak today indeed is much more recent, and which has the idea behind of all this activity is connected to trying to understand how much tools developed by the AI community in generating complex data sets in a stochastic way. So having a stochastic process that starts from pure noise and then it's able to produce some non-trivial data sets, how much these tools might be indeed useful for research questions in our field. Well, for our field, I mean, in particular today, Lagrangian turbulence. And the idea, okay, this is mainly the work is done in collaboration with the people that you see here below. Most of them are in Vergata with me, and then I will also speak about a recent application that we did concerning reconstruction of trajectories of drifters on the surface of the ocean, thanks to the data from Luca Centurioni, who is in California and San Diego. And the aim is indeed trying to I mean, is twofold. On one side, we would like to understand how much these tools that are, of course, very powerful for many applications. In this case, for instance, is the case of trying to generate fake Hollywood stars to avoid paying copyrights. How much these tools that are, of course, very, very, very powerful can indeed be benchmarked in a very quantitative way by using the kind of metric based on statistical mechanics that we are typically using in our community. And therefore, I mean, trying to really go in details and to understand how much the small details of your distribution is indeed well reproduced by this kind of generative tools. And the idea is really simple, having a stochastic model, a stochastic process that is starting from pure noise, so it's very easy to sample because everyone is able to sample pure noise, and then having a stochastic process that brings you in slowly, and we will see how slow, to some target very complex probability distribution. In our application, this instead of generating Hollywood stars, we are going to generate either Eulerian configurations of turbulent flows, or, and this is what I'm going to speak today mainly, or Lagrangian trajectories. And the Lagrangian trajectories is, I think, particularly interesting because maybe this I will discuss a little bit later on. One of the big drawbacks of these AI tools is that they need big data in the sense that they need many samples. Each sample must not be indeed very big. The opposite. If each sample is very big, then the tools do not work because you cannot feed a 1,000 cube data set in a neural network. It's too big, the input. So they need the big data in the sense they need many samples. And therefore, the case of Lagrangian turbulence is really I think at least the optimal application because each sample is very small. A Lagrangian trajectory may be 2,000, 3,000, 10,000 times long, where times I mean the typical time of the turbulent flow. So it's a signal that is 10,000 double numbers. which is, I mean, much smaller than what you would, on the other hand, need when you look at Eulerian snapshots. So it's really, this is the only thing that was indeed the winning idea from our side was trying to apply these tools on Lagrangian data, I think. But from this we can that allow us to go much beyond the proof of concepts. I mean, the kind of application that I show you today is indeed a research question. I mean, we use the tool such as to answer questions that nobody was able to answer using other tools. Indeed, I mean, we were very happy because we succeeded last year thanks to this idea to apply the tools to Lagrangian turbulence to go on the cover page of National Machine Intelligence. And for those of you that do not know what is a Lagrangian turbulence, it's a very simple idea that is a very simple problem in principle, conceptually. You have the Navier-Stokes equations that evolves your turbulent flow. And what you want to understand is what are the statistical properties of trajectories that are advected by the flow. So the equation of motion of the particle is apparently very simple. The velocity is the velocity of the underlying fluid, but of course it's very complex because the underlying fluid is a mess. And but it's a one-dimensional cut inside this enormous dynamical system that is described by the Navier-Stokes equation. And just a very short recap for those of you that do not know, but probably you know better than me, why the problem is physically complicated whenever we speak about the turbulent realization of the Navier-Stokes equation, is that the turbulence, that is the dynamical state that is developed by the Navier-Stokes equation when the Reynolds number is very high, so when, for instance, viscosity is very small, it's a multi-scale problem. So you have these strongly nonlinear structures, and in particular vortex filaments and other topological structures like vortex sheets and things like that, that appear in a multi-scale way. You can zoom inside the one region, you find more or less similar structure. You zoom more and more, and you still find a lot of these nonlinear fluctuations. And when I say multi-scale, I mean typically it could be 3-4 decades. Easily could be 3-4 decades. So it's a system that has in principle a very high number of degrees of freedom that are excited. And the second reason is not only multi-scale, but it's also highly non-trivial. If you do a cut of the velocity field inside your Navier-Stokes domain, the velocity field is very rough. Typically, it's a function that is order continuous with an exponent of 1/3. Indeed, it's even more complicated because the exponents might be not always 1/3. So it's, I mean, you immediately understand that generating signals like that is not easy. And not only is multi-scale and rough, but also it's all strongly non-Gaussian. If you look at the probability at the PDF of the velocity increments at changing the distance, so you look at the velocity here and here, and you calculate the excursion, and then you change the distance, you observe that the PDF goes from being almost Gaussian. This is a parabola. This is a log line. And then by decreasing the scale, so looking at fluctuations that are developed at smaller and smaller scales, the PDF becomes strongly non-Gaussian with fat tails and with easily, here there is normalization is not seen, but is normalized with the standard deviation. You can easily measure fluctuations that are 40, 50 times the standard deviation. So is a very wild phenomenon. It's a stochastic, it's a multi-scale, it's rough, and it's a strongly non-Gaussian. Probably is the wildest classical physics signal that you can find around us, because it's not easy to find other examples where you can indeed have the fluctuations.
You cannot resist to ask not one but two questions.
Yes, of course.
First, then you mentioned the common sense is that with rough signals using activation function which are smooth, you should have problems. No. Learning a non-smooth signal should be wrong. Yeah. Second, the non-Gaussian statistics also should be wrong. You can answer at the end.
Yeah, okay. No, I mean in principle the first question is not a big problem. You have indeed even a theorem that with a deep enough neural network you can reconstruct any function So it's,
there's no smooth
it's not in principle a problem. It's not principle a problem. And the non-Gaussianity, I mean, non-Gaussianity is indeed the real tough aspect. And what is even more complicated is that the degree of non-Gaussianity changes. This is very important. This is the very difficult aspect. Because if you have always the same signal at all scales, at the end you need to learn only one process and then zoom in. While here, that is really the core fingerprint of turbulence is that the degree of non-Gaussianity is changing. This is really so it's not self-similar. The signal is not self-similar. Ciao. So, but this is the background. This is the Eulerian flow. Then the problem is that we want to understand what are the statistical properties of a particle that is navigating, right? That is affected by this flow. And typically you measure. But before showing you the signal, let me say why you want to do that. Why it's interesting. So it's interesting for many reasons. Well, the first is indeed. I mean, if you have a stochastic process that is able to generate your signal, you understand what the stochastic process does, you might be satisfied. You may say, okay, I understood the physics, right? This is not going to be indeed an achievement for us, because I'm going to show you that we have a stochastic process, but we don't understand what the machine does. But on this I will come back, because I have hope that this can be overcome. So this point is really the basic motivation for us at the moment is still out of reach. But then there is, of course, once you have this, why you also would like to have a stochastic process? Because you can do that augmentation. So you have, I mean, if you want one trajectory more in your data set, you should go either on the lab and repeat the experiment, or redo the numerical simulation, which means to resimulate the whole flow. While if you have a model that is, let's say, light or easy to run, that can generate as many samples as you want, this might be very useful for that augmentation of your data set. And then the other reason why you would like to have this stochastic generator, and this is what I'm going to tell you more later on, is that if you know how to generate the signal unconditionally, then you should also be able to do in painting. Right? That is, you might be able to generate. Suppose you have a signal where from time to time you have blanks, so you don't receive your signal. You cannot measure. Your CCD camera is wrong, or whatever. There is a cloud that does not allow you to see what you are measuring. Then, if you have a stochastic generator, unconditional stochastic generator, you can use it to refill, because you can make a conditional sampling with respect to the data that you have, and you refill the gap. This is exactly what ChatGPT does, right? You ask a question, and ChatGPT answer. You ask another question, ChatGPT answer in a way that is correlated, hopefully, that is stochastic and correlated, hopefully, with the data, with the question that you have posed. So why? And I will show you an application of this imputation for data that are data from drifters on the surface of the ocean. So why let me now convince you why the problem is difficult. So why it's really a research question. The problem is difficult also for Lagrangian trajectories, so simple particles that are affected by the turbulent flow. Because from time to time, look at, for instance, at one example here. This one trajectory of one particle evolved as a function of time, is the velocity one component x. You see that the particle, of course, fluctuates up and down, and then from time to time enters in regions where the fluctuations becomes really order of magnitude larger. If you measure the acceleration, this derivative of this course, you see that you have an acceleration order 1 and then might become order 200 and 300. These are due to very small vortex filaments, very small tornadoes that exist in your turbulent flow, and where the particle is trapped there, it starts to oscillate in a crazy way. For instance, if you measure the acceleration PDF, you see exactly the same non-Gaussianity that I was showing before for the Eulerian field. The acceleration normalized with its root mean square can easily reach 40, 50, 60 times the standard deviation. And to give you an idea of how far we are from controlling analytically this kind of PDF, the black curve is what we can do on the basis of a sort of mean field approach. That is the famous Kolmogorov theory and things like that. I mean, we do not have analytical tools, real analytical tools that are able to move this prediction from the observed data, which is, of course is a big problem. Typically, what we do to measure, to observe, to have a quantitative metric to understand the properties of the Lagrangian turbulence is, for instance, measuring the flatness of the velocity increments. So what you measure is the moments of order 4 divided the moment of order 2 to the square. This is a dimensionless number. It's good because it does not depend on your reference velocity field or the amplitude of your reference velocity field. This is a dimensionless number that is, and it depends only on the increments, how distant the two velocity fields are measured from. And these are numerical data. This the black curve, just to give you what you observe. You observe that this kind of flatness, this observable is equal to 3, which is the Gaussian value. When the time lag is very large, that's you expected because they are uncorrelated, the velocity field, if you take them very separate apart. But then when you start to go and to decrease the time lag, so to increase the frequency, the flatness, as we saw before, the statistics starts to deviate from Gaussianity and deviates in a monotonic way, becomes more and more and more and more non-Gaussian until you reach a plateau where you enter in the viscous scale. So here there is a lot of physics. We understand a lot from a qualitative point of view why it changes in this way, but we do not have any stochastic model able to produce a signal that has exactly this shape. So up to now, the only way, in some sense, if I oversell a little bit, the only way to have signals that superpose with this curve is either to redo the direct numerical simulation under 2 million CPU hours, or to go in a lab and to redo the experiment. And for instance, well, then I don't want to enter too much in details. I mean, because by chance, it happens also that these measurements are also the most accurate measurements that we have in our field. I mean, for a series of fortunate events, both experimental people and the numerical people in the last 20 years have learned how to do experiments and numerical simulation of these Lagrangian things with such a high accuracy that we can move from the typical log-log plot that you use to plot the flatness, which is a plot that changes on a few decades, 4 decades in time and a few decades in intensity. We have data accurate enough to measure the local slope of this curve. So to move from something that changes a factor 100 to something that changes a few digits, you see, a few percent. And the data, they have a lot of physical information on the local slopes as a function of tau, and there is a very high accuracy in measuring this data. So this is not only a very complex physics, but it's also extremely well measured. We cannot, I mean, you know, in critical phenomena, you say, okay, I want to check the critical exponent of Ising in 3D. You have a log-log plot at 4 decades, and you end up with a number. Here, we do not make any fit. It's a measurement at every time of the local slope of this curve. So it's just a.
So since you have deviation 10 of 50 sigma, is the flatness enough, or you need to
No, you should make also.
But they are very difficult to measure.
You should measure also higher order moments. The statistics that we have now, state of the art, DNS and experiments, allows you to reach up to flatness of order 8. Beyond 8, this course becomes out of control. Yeah. But no, I mean, in the paper we show also up to p equals 6. But just, I mean, the idea is for the physicists, the idea that really the message that is something that people in the AI community do not capture is that it's really we need to be satisfied. We need to reproduce the signal such as it follows this curve. I mean, otherwise it's useless. I mean, that's just okay. That's a summary of the of other stochastic methods used in the last 30 years. Stochastic methods have a big advantage. They are interpretable. I mean, these are, multifractal superposition, random cascade of wavelets, the infinitely differentiable stochastic process. I mean, many people, including us, have tried the last 30 years to have stochastic models that are able to reproduce this kind of signals. Many of them are very good. Many of them are very good, but none is really able to reproduce this curve with this accuracy. Many of them are very good because are optimized either on this region or on this range or in the very small tau region. But I mean, none of them is able to follow with very high with the needed accuracy this kind of curves. So what we did, we tried to use the state-of-the-art model to generate data in the AI community. And the model that we use is based on this idea of the diffusion models that goes back to a few years ago. Indeed, started to be used by the community no more than 4 or 5 years ago, and it's so simple and so clear. The idea behind it that it really deserves to be discussed, because it's any physicist would understand the beauty. And the idea is the following: we want to have a stochastic process starting from pure noise. I mean, we are all very good in adding noise. This is very easy, right? You start from an image. At the initial time, the image is given by some value of your pixel. You put them, you evolve each pixel with an Ornstein-Langevin process, an Ornstein-Uhlenbeck process. You wait long enough, at the end you will have Gaussian noise. I mean, you can prove it analytically trivially, right? So the process of doing the opposite of what you would like to do is very easy. You just add noise. We are all happy, all able to do. The idea of these guys is to say, okay, so we might have it's very easy from a training data set to generate this forward process to add the noise. Let's learn from data how to invert it. So at every, I will have multiples of my original data set with a little bit of noise, a little more noise, more noise, more noise, and more noise. I have all these data sets that I prepare because this is supervised learning. So I must start from some data set that I want to reproduce. And the idea is that I add a lot of more and more noise at every time step. At the end, I will have pure noise. If I'm able to invert, then I am on business. That you should be able to invert, you know, mathematically, because you can invert the Ornstein-Uhlenbeck process. So you can invert the Ornstein-Uhlenbeck process, and it's very easy to understand what you need to do to invert it. You need to add a drift, because you need to drift the noise towards your final target. And the drift is a force, is the logarithm is the derivative of the logarithm of a distribution probability, and the drift depends on the distribution probability of your noisy data.
It's an adjoint Fokker plan.
It's an adjoint Fokker plan. Of course, this drift you do not know, because you do not know what is the distribution of the noisy data. You only know the distribution of the final point. And so you need to learn this drift with a neural network. This is the idea, so simple, of the people that have invented this diffusion model. The question, of course, is if you succeed, if you are able to learn it, because these are highly non-trivial probability distribution functions. But the very smart idea is that not only you need to learn this PDF, but you do it step by step, because you always need just to move from some noisy data to some data that is slightly less noisy. So at every step, you need to learn a denoising that is due to a very small original amount of noise addition. So this is the big advantage of this diffusion model with respect to other data-driven models that already existed before, like a generative adversarial network, is that the generative adversarial network do exactly the same, but in one step only. They do it with a...
Do you assume there is a single stochastic process that can generate or you could have in principle several different stochastic processes?
No, but you assume that you want to learn the stochastic process that you have used to make the data more and more noisy. So you might go from year to year with a different stochastic process, but you have done it because you
know there is one. There is just one.
Yeah,
one out of many.
You know that at least you want to learn that one. Okay. Another thing that is important for physicists to understand is that you have a data set for training. This data set is a finite number of samples. Right? It could be 100, 1,000, 1 million, but it's a finite number. So the PDF of the data set, of the training data set, is very easy to know because it's the sum of the delta function on those samples. But you do not want to learn that PDF because if you learn that PDF, you just memorize. You just learn how to start from noise and to end up in that PDF. So the process that you want to learn, because the network will not be exact, will not be able to learn this very complicated manifold with 100,000 of delta function, the process will make an error, a small error. The neural network will make an error, a small error, which means that it will interpolate around this delta function, and this is what you really want, because you want to generate samples that you have never seen. I mean, if you learn exactly your training set, you are memorizing, and it's completely useless. Right? So the idea is very strong because you use this process that is very stable. No, it's a Fokker-Planck evolution, and you want to train it to be close to your training data set, but not identical. That's and there are these people now. The people study this transition between memorization and the generalization, which depends on how many data sets you have, how big your network is. It's highly into statistical mechanics.
That's why they stop the convergence ahead of time. Right?
Yeah. Yeah.
No, we just you put in a way that you somehow exploit the errors that the network does.
See.
But if put in this way, I mean, you have no control of the errors, so you have no control of how the extrapolation of the data is then.
On the extrapolation, you don't have any control, and I don't trust it will extrapolate too much.
I have a question for you. The function, the f, it depends on t.
Yes.
It depends on
t on the step of the diffusion program. Yes. Yes.
So you have a timing.
You have that's why it's very slow. I mean, the generating process is very slow. The people in the AI community do not like at all. I mean, that there is a big commercial effort in speeding it up. Because
you not imagine a general function, because the process is a step-by-step process.
But there is no reason why it should be time. It should be stationary in time. I don't see any reason. At the beginning, because what you want to produce is not self-similar in time or stationary in time. You want to produce a signal. I think I have it. It's very nice to see how it produces the signal. It is non-stationary in this diffusion time, this diffusion step.
Also because there is a clear start and a clear end. You start with something structured, you end with something completely unstructured, so it's non-stationary.
Yeah. So that's yeah, but you can do it by a stationary increment. But it's not even because David is speaking about the stationary increment. Because every time you do an increment, right? So you can do it in principle, but the system is strongly on. So it depends on time. I mean, it's you need to make it depend on time. Okay, so what we did, I mean, now it's clear. I think we just now our data set is trajectories. We have 100,000 of trajectories. And we take the initial data set, the training data set with 100,000 trajectories. We start to produce other training data set with more and more noise. This is the forward process where you add the noise. And then with a neural network, you learn every time how to go back. You hope to be able to learn every time how to go back. And there is a lot of machinery, a lot of tricks. If you can do it, it's better to do it uniformly. If you need to change the standard deviation, I mean, it's a mess. There is no clear recipe. You need the people that have spent time. Fortunately enough, I mean,
many different
it's a mess. I mean, I don't control the fine tuning of the hyperparameters.
How many do you have?
Sorry?
How many hyperparameters?
No, the network is 20 million parameters. But then it's not only you need to decide the scheduling of this. I mean, because the time step, I mean, it's very inefficient to have the same time step in terms of the diffusion process, because at the beginning it's only noise, so you want to go faster. But then if you go too fast, it doesn't. I mean, it's a mess.
But you are in the overfitting regime. You have more parameters than data.
No, I mean, but because data is I mean, trajectory is a 2,000 long trajectories, right? So 100,000, but they live in a space, in a dimensional space that is a 2,000 dimensional. So it's and as I show you, all points are important because the physics changes with tau. It's not a smooth function.
But right? The reason I ask is one of the big discoveries, quote unquote, of the large language model is that they can survive overfitting. So my question is whether you are in overfitting. No,
we are not in overfitting. We are not in overfitting. I will come back to that because it's an important question. So just to give you a few results, statistical check. So we tried, after some failures, we succeeded. And just to give you an idea, a visual idea, this is like the computer, the AI community would do it. These are, trajectory, 3 components of a particle, one trajectory from the ground truth. This is another one generated in a fake way with our model, just to show you that there are the correlation between the components. It really learns how to, in some sense, the non-trivial structure of the system with the vortex filaments, and it is really very, I mean, at least visually very similar. Then, if you check in a more quantitative statistical way, these are the black line are the PDF of the velocity increments. Again, you see with fluctuations up to 20, 40, 50 times the standard deviation. So the black line is the ground truth. DNS for me is ground truth. It's our original signal. And the blue line is the diffusion model. And you see that not only the PDF superposed, but here there is a very nice fact, which is in part connected to what Massimo asked, that because once you have the model, you can generate as much as you want or as much as you can, because it's very slow. But I mean, so we generated something like 20 times more the statistics of the training. And you see that it extends the tails in the right way. So it produces events that with an intensity that has never been seen in the training set. It is true or not, of course, this is a question that is a problem of induction, that is, you never know, right? I mean, even general relativity, you don't know if it is true when you don't measure, right? So it's, but at least, I mean, it's not, one could have expected something like that immediately a failure, right? To not produce anything. On the other hand, it extends at least visually in the right direction. And then you might have, this is what I want to tell you, David. This you can see how it builds the signal, right? During this denoising. So the final signal was this flatness. At the beginning, everything is Gaussian because you start from noise, and then you see that it starts, of course, to feel the large scales, and then to feel some more and more the large scales, and at the end you are very close to the ground truth. How close you are to the ground truth? Well, pretty well. Here I show, for instance, the flatness up to p=8. And forget the orange one. It was a previous attempt that didn't work so well, but then we improve it, and let's look at the blue one. And you see that this is the flatness of order 4, 6, 8. Is pretty good. It's much better than what we had with the previous stochastic process. There is a small smoothing at very high frequency. These are at the end. These are always interpolators. So it's I mean, I don't claim that one cannot do better. Probably one, by improving the hyperparameters, one could do better, but I mean, we didn't even try. We were very satisfied with this. And this is the kind of measurement that I was mentioning you before, that is a key step for us, for our community. I mean, I could not publish a paper like this on a turbulent community without showing a data like that. And here you see the black line are the black dot are the DNS. And the blue is the local slope. It's a measurement. It's not a fit. It's the local slope on 4 decades in time of this course. So we have a precision that is below a few percent, 2%. So this was really, I couldn't believe when I saw it. Then let me show you a few applications. One application, and then I have a few comments, general comments. Application. So then is now there is the interesting part, because to have a stochastic model is good, but it's relatively interesting, because then you have to say, okay, now what do you do with that? And here is we played to refill gaps in real data. So we supposed to have, we took the data from trajectory of drifters on the surface of the ocean. There are thousands of these trajectories. They are extremely noisy. These are really messy. These are real data. So these are the drifter that goes on the surface of the ocean. Every hour send the signal by GPS to the satellite about velocity, salinity, temperature, and so on and so forth. And the drifter, from time to time, they disappear. The GPS does not work. I mean, it's a data, very dirty data. And so what we played the game is to have the trajectory. Of course, this is again supervised. So we first needed to select the trajectories where we have data everywhere. And then we played the game. Okay, let's remove data in the middle. Here there was a movie, but now I cannot show it. And so the idea is that you don't have data in the middle and you want to refill it. So this is a conditional generation, which is much more complex in principle, and it's much more important. So it's like if you have the three-dimensional trajectory and then you miss some data and you want to refill it.
ChatGPT-4.
Exactly. Yes, this is what ChatGPT does in some sense. And okay, there are many different ways to move from an unconditional generation to a conditional one that are, I don't think there is too much to say. The simplest is just to close your eyes. You use the same network and you show in input part of the data that you want to, part of the signal where you have the data, and you put noise all in between. This was the original option. This is really the simplest. And it works pretty well. Now there are better tools, we, in order to have a benchmark, to validate against other tools, what we always compare is also the capacity to refill the gap by supposing to have. Oops, sorry, there is. What is that? Okay, sorry for this mess. It is not anymore filled. No, yeah, that's no. This was supposed to go on top of the bottle. Okay, so what we say is that we always compare the generative, the conditional diffusion model with, for instance, in this case, a Gaussian refilling. You already understand the Gaussian refilling will not work well, because data, also the oceanic drifters, have a stronger non-Gaussianity. But nevertheless, the Gaussian refilling is one of the few tools that people in the community add to refill the data. And the Gaussian refilling is simple. You're supposed to be Gaussian, you measure the correlation everywhere, and then you do the conditional, using bias theorem, the conditional refilling inside your gap, supposing that you know the two-point correlation function. And okay, this maybe is not too much interesting. Just to give you an idea, here we compare. So then we tried by changing this the position of the gap, and just to give you an idea, this is the mean square error inside the gap. So this is not a statistical metric. It's really a point-to-point metric, because it's the L2 distance between what I reconstruct and what I see. And the purple is the Gaussian refilling. The green are the conditional diffusion model. There is a small improvement in the diffusion model, but it is not so impressive with respect to the Gaussian. And this is not surprising, because the mean square error is a two-point statistics. So the Gaussian process, it's always very good in fixing it. What is surprising is when you look at the high orders. So for instance, here is the flatness. Forget about this. This was our benchmark for the 3D isotopic case. This is look at this picture. This is the flatness measured on the oceanic drifters, and the black curve is the real data, and the green is the one that we generate. by refilling the gap and by doing a fair test, because we always took one data in measuring the flatness, we always took one data outside and one data inside, such as to really be sensitive to the correlations. And the diffusion model is really very close to the ground truth. If you use a Gaussian process, it's of course on the Gaussian baseline. And what is interesting is that the model learns, because you imagine that the oceanic drifters are strongly non-homogeneous, right? If you are at the equator, it's much different than at the Arctic. Right? And but when we train, we don't say anything; we just show everything. But when you refill, the information of where you are is hidden in the data that you have given. So if you can check how much the model is able to distinguish on the data that you have, whether it was on the western boundary currents, on the tropic, and you see that despite of the fact that the statistics changes, the model is able to follow it. I mean, not perfectly, but it's able to follow.
How large is the typical gap in this data in time?
Can be whatever you
Can be
want.
whatever. And the second question.
The main problem there is that sometimes they lose the drag, the anchor, and then they completely change the statistics because they are advected by the wind. I mean, data are. I mean, if you think that they do climate prediction with this data, you are worried.
No, and the second thing, I wonder if I mean, some oceanic currents are well characterized.
Yes.
So in principle, and there are also general circulation models which run them and so on. I wonder if the trajectory that you reconstruct conform statistically somehow to what you would expect the currents would move the. You see what I mean? If
this is what we do in some sense on the real data, because here we compare only with drifters on the tropics.
Okay.
Right? So this is what we do on the real data.
Okay.
And then if also a model for the tropics currents reproduce the same statistics, this I don't know indeed. I mean, but this is a problem more for the model than. I don't know if people ever look at these things.
But because this is a time.
This is along the trajectory.
What I wanted to point is if you can reconstruct also the space, because if you,
with this tool I can't, because this reconstructs one trajectory at a time. So you do not have any way to infer the spatial distribution. You see?
Yeah, but I mean, if you reconstruct the position as a function of time,
yes.
What you do, in principle, you can track the movement.
I show you. Wait 1 second. Maybe okay. This is about extreme events. Here there is a very subtle thing that also surprised me. Let me spend the 5 minutes. That also puzzled me because I thought it was wrong. Because then, for instance, here we were checking about how good is the model to predict the most extreme event. So independently on the gap, where the extreme event is in the gap, if it's able to, from the data that I show you earlier or later, tell me that inside where I didn't measure, there is a very big event. And this is the correlation between what the model predicts and what we observe, which is pretty good. And this is the correlation that you would see by using the Gaussian regression process that you see is completely wrong, completely incorrect. But what really puzzled me is this case, the C3, because here we check, because the model is a stochastic reconstruction. So you give the same signal and gives you different answer. It's correct because the physics is stochastic, like ChatGPT. You ask the same question, it gives you different answer, right? So the fact that it's stochastic is good, it's very good. But then we ask, okay, let's take a case where the ground truth had an extreme event inside the gap, completely masked. You see, if you see before and after, you don't see anything. It would be very difficult to guess that you have something. So I was convinced that the model would have failed. And this is the PDF of the events that are reconstructed by the model inside the gap for that particular case. And this is the one observed. And you see that the model is still able to tell you that what you observed is within the capacity of the model to predict. It is a very, very far tail, but it is consistent with the statistics of the diffusion model. If you would have used a Gaussian regression, this is what the Gaussian regression predict. I mean, Gaussian regression would have never, out of these statistics, be able to say that there is a chance to see a 40 deviation, 40 standard deviation event. I mean, the model is able from this smooth fluctuation understand that inside there might be potential very strong events.
You can see this graph also the other way around. Instead, in the case C1, you see fluctuation much bigger than the one in the real.
Yes, yeah.
So you have
Yeah, exactly. But there the Gaussian model is not too bad. There the Gaussian model is not too bad because this is the diffusion model, this is the ground truth, the one observed, and the PDF is perfectly inclined. The Gaussian process is not so far. But this I mean, I mean, it's
principle tested also on the simulation because now I made it feed with all of the trajectories.
yes.
You can like feed with the selected.
Okay, this is what we are trying to do now. I will tell you more. I will tell you more about that. Yes. This is maybe you must answer partially your question. Then, of course, once you have the model like that, you might have a stochastic reconstruction of the trajectories, right? Where do they go? And so you suppose to have, you know, a drifter that at some point you didn't measure, and then you see what is the typical distribution that you would predict the drifter as followed inside the statistics. And we tried also to have some quantitative comparison, even though it's not so clear how to do it quantitatively, and we were pretty satisfied. But let me then move on a few technical aspects that are disconnected from the application. So forget now about the application. Let's go back to the tool. And the first take-home message that at least we learned recently is how to distinguish between memorization and generalization. Right? So we wanted to have a clear statistical test to be sure that we are generalizing and we are not just memorizing the trajectory that I showed. And the best way to do it, I mean, one way to do like that is the following. As I said, when you learn how to interpolate a distribution that has been sampled by delta functions. So what you would like to say is the following. Suppose I use half of the data to train a model and the other half to train another model. If the model is learning the right interpolation, even if I show two different data sets, the model should be the same. This is a model with millions of free parameters, so it must converge on the same model independently of the data set, if you are generalizing. If you are memorizing, because we have shown two different data sets, you would have two different models. So what is the best thing to do is to say, okay, now I train on two different data, I split my statistics on two data sets, I train on two samples, and then I use, even though the model is stochastic, so if I show the same noise at the beginning, it will produce a stochastic trajectory. I will produce two stochastic trajectories with the same noise, such that if the two models have learned the same map, they will land on the same trajectory. And this is what I show you, what we did. This is an example starting by giving the same history of noise to the two independently trained model, and you end up in these two trajectories. These are the three components. We always show the three components. That, I mean, if you look at them, I mean, they are clearly very, very similar, right? And then you can quantify. You can quantify the cosine difference. And the cosine difference, you see, it has a distribution much very peak to one. So this is a very strong test that you are generalizing. The other thing that
how do you say pick the two data sets, the two subset? Because obviously you may have a different distribution.
Yeah, if you do like that, and we did at the beginning, we did like that, and it was not generalizing. You need to do the data set that are homogeneous with statistical.
So you need to do a sort of a process.
Yeah, you need to know what you show to the two models. because otherwise they will learn.
Otherwise, you should do a huge work to make multiple samples.
Yeah, but in our case, it's pretty easy because the trajectories, they go around the flow. So, and we know how to label them in terms of initial condition. We know at least how to split in two sets that should be statistically. I mean, of course, if there is a bias in the original data set, that bias, I mean, it's you learn the bias. And then, if you want to have also a benchmark, you see, okay, let's see how a trajectory that I generate is closer to all the other trajectories in my training data set, and then you expect that it should not be picked to one because you want to generate something new. And indeed, the distribution is not picked to one. And the distribution of what you generate is the same typical distance that you have on the trajectories of your original training set. So it's really you are really reproducing the same similarity also inside your. These are the two, the green and the yellow. So this was very nice. Then there are other tools that are very interesting indeed, that is connected to the extreme events, because now people have learned how to do this generation in a guided way. So what they do, suppose you want to refill the gap, and you have the black line here and the black line here. A very efficient way to do this data in painting is to allow the model to generate the whole trajectory, but then you put in the anti-diffusion a drift term that tends to push your generation toward the data where you have the data. This is very robust because you generate everything and you gently, more or less gently, guide the generation such that the mean square error between what you generate and what you have is very small in this region. This is very good because it allows you, for instance, we hope at least, we are trying, but we don't know if it works, to generate extreme events conditionally, so to do importance sampling. I mean, we hope that in this way we are able to put as a guidance to have a, very high flatness, and therefore to do important sampling only on the tails of the distribution. This is what we are trying to do now, but we don't have results yet. So then you can use it also in the loop, that is to generate forever, right? Because it's like if you have the gap in the second half, then you generate the second half, then you plug the second half in the network, you generate, and you go on and forth. And this is more or less all what I wanted to show. Of course, you can apply to many other Lagrangian things. Let me send again the message that the Lagrangian application, I think, is smart because it combines the complexity of the signal without the fact that the signal is big data input, and therefore allows you to benchmark these tools in a very quantitative way. I mean, the same degree of benchmarking with a three-dimensional configuration in Aristotle would not be possible, because I cannot have 4 decades in the original field. It means 10,000 cube. I mean, first we don't have the data for training, and second, even if I have the data, we don't have the GPU, so it's impossible. While here you can ask good questions with a limited amount of input data. And then, okay, we have tried to other applications. The other message for physicists is that we are also working a little bit with a group at the Collège de France, of Stéphane Mallat, who is trying to do a further compression. That is trying to first compress the data using interaction between wavelet coefficients, and then learning a potential for these wavelet coefficients. And this boils down the problem from 20 million free parameters to a few hundred. First. And second, it gives you the interpretability, because once you have a potential between wavelet coefficients, maybe you might understand 600 parameters maybe it's not so easy. But nevertheless, better than 20 million. Okay, then just a take home. I mean, as I say, the explainability, we are very far. Proof of concept, this Lagrangian framework allows to go beyond proof of concept. This is not Lorentz system. And the generalizability, we have of course, I mean, if you change the training sample, everything changes. There is no issue. And this generalizability is inside the sample. For in sample, at least for what we tried, it was not that bad. I mean, it was indeed we had a positive feedback. What is very upsetting, at least for me, is that the scalability. I mean, at least I do not have any way to predict. Now you give me a new Lagrangian data set with Reynolds 10 times larger. Do I need to use 10 times more free parameters, maybe 3 layers more? I mean, completely every time, at least for us, but I mean, we see also what the community does. You start from the previous one and you start to
But actually, there is this famous story about scalability in large language models by OpenAI and I just looked recently. They show scalability. They responded to 0.1, less than that.
But for
large language models.
Oh, okay.
And they make big claims about 0.1 is totally unsustainable.
No, I have no idea. I mean, but I mean, they show in the sense that they measure. Sure, if you measure, and that's. But I mean, I would like to. I mean, if I give you a Reynolds number and I ask you, give me a lattice-Boltzmann code, you tell me exactly a priori, right? What is the tau that you have to use, the delta X that you have to use? Here, this knowledge is completely out of control. Completely out of control.
Strange, because you seem to be doing very fancy things.
But I don't know how to dimensionalize the tool with respect to the complexity of the problem. There is this link that is fully missing. Unless I measure, of course, if you give me data sets at different Reynolds number, I measure how it scales, I tell you, okay, it scales. But I mean, on the other hand, for lattice-Boltzmann, you have an understanding of why you have to reduce delta X, why you have to reduce tau.
For lattice-Boltzmann,
for any algorithm, you have a prediction.
Well, actually, any algorithm you can see the other way around. It's a machine learning with no need of training. Actually, any algorithm, the one that you use,
sure, but I mean, what I'm saying is that it's really difficult to understand the structure of what you're using and make a.
Let me give you a little example. It's not published yet, but I went in a lot of time, right?
Yeah.
We did a pin on a simple Monte Carlo to learn another 5 graphs. And then I asked the guy to show me the weight matrices, 10 layers under the overlay. And the weight matrices are basically Gaussian. So there is no memory whatsoever of the structure of the problem. So I'm coming to the conclusion that explainability is a failure.
Is that?
These models cannot be explained, at least by our mind. It's 2 different paths to knowledge.
I mean,
explainability.
I mean, I have very little understanding, but explainability to me goes first through the subsampling and the projecting on explainable eigenfunctions, because otherwise, the brute force structure. I mean, also we tried at the beginning to look inside the network. And you do all these ablation studies, you remove something to understand how the network reacts. But I mean, it's so qualitative. It is,
but there is no way you can look at your weight matrix. No. Why not?
I mean, but there is. I mean, you can look, but then you have to ask the questions about. I mean, what we tried is to have this sort of reverse engineering, right? Remove some part to see how the network changes.
Well, this is for uncertainty.
But I mean, even that way, I mean, if you look at the network, it's okay. It's impossible, at least for us, to rationalize what it does.
I think it is, but by very principle. But I don't know.
Just curiosity. In principle, we can do this approach also to work with the couples of trajectories.
Yes, indeed.
Because, I mean, in turbulence, if
We
trajectory
did-
evolve within the same flow,
we did with Kibaro, but I could not present the results because of Kibaro. That is still in his messy cloud. Huh?
You cannot present Kibaro.
Yes, you can do it. It's interesting for two because the system there is non-stationary. While we need to produce a system,
exactly, because
because
we have the
they
diffusion
need to learn. It learns pretty well. It learns pretty well. Still, we have a problem in. Apparently, is interesting. We have a problem in learning those pairs that do not separate much. So the tail, in principle, is the most should be the easiest. There, the model is at the moment is failing more. I think there is a problem in the way Cedric is doing, but anyway, let's.
It would be also interesting because you can also test if the model learns the Eulerian statistics.
Yeah, sure.
Because you take.
It must learn.
It must learn. Which is, because since you have all the problem you described, using the hypercube, this would be a Lagrangian way to reconstruct the.
Yeah, always 2 points. Right?
Yeah, always 2 points, of course. But I mean, such a function is 2 points.
Yeah, sure. I agree.
Other questions? Questions from the online audience? Looks like there are no more.
No. Okay, thank you very much.
Thank you for watching.
Riprenditi il tuo laser.
Come si leva adesso?
Come ci si? Ah, ma io, questo è il vostro, per me potete fare quello che volete.
Questo di beccare gli eventi estremi
Questo qua.
Allora, aspetta, terminiamo. Allora,